you were going to talk about how to make databases fast. Is that right?
I mean, yes, like the thing which careers are made out of. So it's um, both like a very simple prospect and also like kind of like the hard problem. Um, and I think I guess like there is only one thing that it's sort of a trick, right? Like it's both this like huge topic and also there is only one thing that we do, which is that we make the database, we like make sure that the data that you need in order to satisfy a query doesn't that fits in RAM. And because disks are slow, certainly 20 years ago, spinning disks were really slow. And even now, though, like SSDs are like pretty fast, if we're being honest, like they're still slower than RAM is. And there are like nuances to this, right? You query result sets can be larger than RAM. In transactional workloads, you do sort of want to make sure that like only the parts of the tables that you need fit into RAM when you're like doing that operation. And so like in transactional workloads, particularly with like high volumes, like it's a sort of more complicated and kind of higher stakes process. And in analytics workloads, the constraint is actually a little bit different because it's like, yes, you want to fit everything in RAM, but you don't need to sort of have this concurrent workload. Like you're both like accessing, making that query less often, probably, and you're not sort of doing transactional workloads, and you're not and again, like the data that you inspect is almost always going to be larger than the amount of RAM that you have available. So it's a slightly different problem, but ultimately, like that's what you're doing. A query that has to go to object storage, that has to go to disk, object storage being, of course, slower than disk, just takes longer. And so the kinds of things that make databases fast are being efficient with how they use RAM, and how they like keep data hot. And there are like classic tricks to this. And they're all like hacks, but like gloriously beautiful hacks. And one of them is, so like the sort of easiest way is that you compress data. And if you can sort of keep data like mostly compressed, it doesn't like you don't like you do sort of have to uncompress little parts of it as you go, but compression means that you're using more CPU to do the decompression, but you're not storing as much in memory. And so that's useful, right? And trading, like CPU is often sort of a more bountiful resource in most computers. So that's like often a good trade-off. The other, and this is a transactional thing, or transactional engine thing, but indexes allow you to perform operations on a table without needing to hold the entire table in memory. And so indexes hold only a certain number of columns plus pointers, essentially, to wherever they are or wherever the actual row is. And so you can store like, if you have a table that has, that's like a gigabyte and has millions of rows, you could potentially have only like like if you're indexing an integer field, you have like the size of the integer and effectively another integer to store the pointer. And so you're like, it's like, like 2 million in64, say, is like very easy to keep in memory. And so you can keep the entire index in memory and then only read out the parts of the table that you actually need to read out as you're going. And that makes sense for row oriented data, but we see sort of echoes of indexing as a strategy in these like modern storage formats like Parquet and Lance, which use metadata, which sort of group the data and provide metadata about what is in each group. And so you can skip through the file and only get the parts that you need. Similarly, so that's like the hack. Also, and this is sort of like in all of these cases, ordering, right? Okay, sorry. Order, the key word for the next little bit is like ordering is important and kind of hard to do, and you should avoid needing to sort things. Is like the sort of next thing that this like keeping things in memory and indexes and storage formats kind of help with. Fast sorts are always, the way to do a fast sort is to not sort. And so you either have indexes which are sorted in a specific order, and then you read the rows out in the order that they appear in the index, not the order that they appear in storage. And so then you not actually sorted anything, and you don't have to keep all of the rows in memory in order to do the sort. And so these indexes are, of course, like you are still sorting because you have to keep the index up to date, and that's expensive as you do transactional style updates, because you then have to update both the data and also the indexes. But you don't have to you don't have to then sort on output. And we have the same basic thing happens in these like analytics focused storage formats, is that you write the data out sorted by some value. So when you create a Parquet file, logically the first column is ordered by some constraint, hopefully. And if it is, then you can, and you know that you're doing a query where you're getting either returning results in a certain order, or you need to sort the order in order to do some kind of grouping or window function or whatever ends up being the thing that you're doing. You can have a data set that's larger than memory, and you only read out either the sections of the file that you need to do because you're selecting a subset of the files or a range of the files, or you are able to read the data out of the files once and allow the data to continue flowing through the pipeline of the query. So like flowing through the processing of the query, without keeping it, like collecting it all in memory first. And analytics databases, and all databases will eventually like spill some of this like working memory to disk for whatever purpose. So it's not as if like sorting in memory is a thing that you always have to avoid, but it is, it does make it faster when you do that. And so, okay, so we've gotten through, just to recap, like you keep data in memory, indexes help, sorting is hard, and you should do it by indexes. It's also a reason that you may write your data out and for online analytics processing workloads, you may actually keep different copies of your archival data with joins pre-computed or with or sorted in different ways, just so you can satisfy these queries more quickly. that's sort of like the big stuff, building the systems which can sort of decide when to, building the systems both as a user and also like as an engines maker that know when and how to materialize what things, and which orders you need to have are important, and that's like a lot of work, and that's why doing that well and transparently to the users is interesting. There is this sort of last other hack that people use, which is basically that you can, for certain kinds of caches, you can like build a cache or some sort of caching layer which isn't actually very smart about what indexes and what is in memory and what gets built to disk. If you write it all to disk, do the memory mapping, you use this like operating system function or libc function called mmap, and that sort of puts the entire file sort of as if it were in memory and lets the operating system manage like what falls into or out of memory. And this is both like really good in the sense that it is fast and it's one function call, and we understand it pretty well, and very terrible in the sense that it works well, and so it is easy to accidentally rely on it in cases where it doesn't actually give you enough control, and then you sort of get stuck with a certain set of guarantees, and building the kind of canonical correct implementation of those kinds of like caches is hard and fussy, and thought isn't great. This is like canonically, or not canonically, really. The original MongoDB storage engine was just a bunch of memory mapped files with like a little bit of concatenate, with a little bit of like metadata and a bunch of like JSON documents, and it was actually pretty great in the sense that it worked really well for a really long time, and it was terrible in the sense that that it's a giant hack, and it doesn't give, there were all sorts of features which the engineers could not sort of build on top of a sort of wacky collection of memory mapped files, and this like gives way to the current, they replaced that, which is good because it was unsupportable and unmaintainable, but it did work, and it was really fast, and a lot of sort of let's use it. It shows up a bunch. I think that like Andy Pablo has a like mmap isn't your storage engine blog post that we could probably link to, that I hope. This is straight from like my own cold storage, so I'm not 100% sure about this, but but like I think like if you are building the right database, you wouldn't do that thing, but there are like little cases where you do want to memory map a file if you're doing a lot of work on it. So that's like one thing that's like a thing that database makers use, or a function that database makers use. And I guess like that's like a lot of sort of how you optimize your queries by hand is to ultimately to project more data, like to only sort of carry forward the data that you absolutely need. And so if you're building queries or pipelines of collections of queries or sequences of queries you will want to, as quickly as possible, like filter and project your data into a much more reasonable set, like data set, which will then hopefully fit in memory. And so by the time that you're doing sort of random groups and sorts, you have something which now hopefully fits in memory. And so that's like that kind of does it. Like everything else is in service of like using the memory, which is really this like finite resource, as efficiently as possible. Being able to like allocate it efficiently, drop it when you're done with it efficiently, not have to do these slow reads from disk or reads from the network unless you really have to. And the more you like use that sort of more local data, the faster you get. And it kind of applies to every system. And that, and then and so this is like this is the sort of thing that's like difficult about this, is like sometimes you don't have control over it, or sometimes the data isn't laid out in the right way, and then you are stuck in this position where you have to use more, like write it out to storage in a way that's more efficient for the query that you're trying to run, or something. And a lot of but a lot of like what you're doing in ETL pipelines is sort of making sure that the data is shaped in a way that will let you do these queries as efficiently as possible. Store the data in a way which will facilitate the query, and hopefully help it be fast. And there are a bunch of database systems which have these have sort of smarter kind of index forms, which are really about finding increasingly like concise ways of expressing sort of metadata for your data set, so that you can read less into memory. And those can be very smart. I think some of the big cloud providers ultimately are building indexes or materializing data in one way or another based on observed query traffic, and so they can get faster for your data over time. And they do that by collecting data about your use, and then writing data as they need to make sure that your queries are fast. So, and that's the trick. That's it. That's all it is a sentence which obscures where all of the hard work is. But yeah.
So let me ask you a follow-up, because I know something that I've heard you talk about a few times before is this idea that like when you look at, I think certainly the analytics databases nowadays, it seems like there are three schools of thought. There are the databases which are really optimizing the storage format, and the databases that are really optimizing the query engine, and then databases which are doing something a little bit different, like maybe distributed execution would be an example. So how do those, and maybe there are more. So if there are more, please say so. But otherwise, how do these three different schools of thought like interact with this notion that it's really just about fitting stuff in memory?
So I almost should like write down what the three are. You said storage format.
Yeah, query engine.
Yeah.
And then I guess distributed execution would be the third kind.
So distributed engines. So there are some classes of query. I'm going to go backwards. There's some classes of queries which are which are sort of necessarily parallel. You're reading a lot of different files or reading lots of different sections from files, and there's nothing, and you're not, and all of your query is like happens before the sort or the group. And so you can do most of the workload in parallel. And so query engines will work to push the sort as late as possible and the limit as early as possible, and the limits and the projections as early as possible. But if you do that, and that's like sort of query optimization or analytics query optimization in like one sentence. So it's obviously like harder, like that's a sort of hard problem. But but if you do that, then lots of the query can be parallelizable. And if you have lots of data, it's more likely, or data coming from different places, it's more likely that you can have that parallelizable query. And so distributed execution basically says for queries which have that property, we will like allow you to have the amount of RAM required be as large as possible. And that's really like what distributed execution says. What if we give you the same query but make the RAM kind of scale up very, very efficiently, or give you this like many very large set of data for RAM. So that's the hack. Query execution sort of falls in all of these categories. Make the query as parallelizable as possible. Filter as early as possible so that you need less RAM. Use indexes as pick the best index to use, or the best like materialization of a data set, so that you can get the, so that you use the right, you are able to use the amount of memory that is available. And there are like knowing things about the shape of your data, where it lives, what the expected latency for a data source is. All of those things can be used to produce like a good query plan. So that's cool, I guess. And the last one, this like storage format, is sort of, if you make the data sort of, then there's this needle of like, make the data very compact without, and so that it takes up less RAM. Compression is an example of this, but there's also various ways of encoding data that can be very efficient. And the trade-off with that like efficiency is that the more efficient it is in space, often the more time it takes to write, and in some cases the more time it takes to read. And so if you do that, like in transactional systems end up being like less efficient storage wise, because they store indexes which take up room, and because they want to be able to write data like very efficiently to disk. And so that like write efficiency is a trade-off with read efficiency. There are sort of these like two classes of databases in the world, these like general purpose transactional systems, and roughly general purpose analytics engines. And then there are sort of two special kinds of databases which sort of have different needs with regards to space and write efficiency and data layout. And to my mind, these are time series databases and graph databases, which are just sort of like time series databases. You have to write a lot of data and it can be very compressed. and you can have to have lots of throughput on your write data. And so like time series databases have to be like high throughput, compressed writes, and the queries don't have to be as fast. Or don't necessarily have to be as fast in the same sort of ways, because you're writing way more data. You're writing more often than you're reading data. And graph databases are like kind of wild and amazing because you're doing this query which potentially has you sort of moving about the data set in a way which isn't sequential. And so having like ultimately like a set of indexes which are arranged in a graph-like way is certainly slows right input, but is a thing that you basically never need in any other circumstance, but it is and in both time series and in graph databases you have like querying is different, and so it makes sense that these are sort of special purpose databases, but the ideas are sort of everything else sort of has like either this like analytics or transactional kind of like profile. But the problems in all of these cases are sort of the same.